Okay, we discussed the static friction force last time. We learned that the static friction force it's not a constant, right? It actually changes with the external force applied on this object trying to move it. But there's always a maximum static friction force from the surface if the same object on the same surface, and that maximum static friction force, we do have an empirical equation to calculate that. It's this coefficient of static friction multiplied by the normal force. Okay, so again, the actual static friction force, if you want to find it, you can't just use this equation to find it. Okay, this only gives you the maximum. Okay, the actual static friction force. If you want to find it, you're going to set up Newton's laws, right? Because if it's static friction force, then the object is not moving. All the forces must cancel out. You set up Newton's laws in x and y directions, then you can find the static friction force, right? Now we want to take a look at a real example with numbers, okay? So we can, again, practice what we have learned for static friction force. So let's take a look at this question on slide 8. Okay. A block of mass 6 kilograms pushed up against the wall by a force P that makes angle theta equals 50 degrees with the horizontal. The coefficient of static friction between the block and the wall is 0.3. Okay, so the problem already gives us this mu s, and this problem is 0.3. Determine the possible values of the magnitude of P that allow the block to remain stationary. Okay, so what does this question mean? Okay, what does it mean? Determine the possible values of magnitude of the P. So we're not looking for like one value. We're looking for a range. How do we find that? We did learn a theory to help us find a range for force, right? This P force. So let's look at it a little bit more carefully. Someone say you're pushing this block up a wall, okay? So again, you can try this experiment, right? You can definitely do this, right? And actually there's a certain range of the force you can apply, not just a unique force you apply to keep this object on the wall, right? Why? Again, it's because the static friction, if this thing is not moving, the static friction, the friction must be static, and the static friction can always vary between 0 to the maximum. So that's why the force you apply on this object to keep it stationary on this wall is also going to be a range. Then, okay, if it's a range, so all we need to do is just find the lowest value and the highest value, then that's the range. Okay, so how do we find these two ranges? How do I find the maximum value? Okay, so think about that. If you apply force on this block, okay, against the wall, but not straight up, you apply force in this direction, and you can keep increase this force and then until it's large enough so this box is going to start to move upward. Okay, so that's how you find the maximum value, right? So what is the minimum value? Again, I'm pushing this against the wall, but if I apply force very small, you see, it's going to slide down, okay? So there is a range. Now, okay, so that's how I figured out conceptually, okay? And then how do I find these two values? I'm going to use the laws and theories I learned in this class and then do the math. Okay, so let's take a look at it. Now we're going to draw a Fibber diagram because I'm trying to find, I'm still finding a force. I just want to find the maximum P force and the minimum P force in this question that will keep this block stationary on the wall. So I'm going to draw the Fibber diagram of this block. So when I draw a Fibber diagram, the first force I draw is always gravity, okay? And then in this case, there's a force P applied on this wall, on this block, in that direction. So when I draw a Fibber diagram, I usually draw all the forces starting on the center of this object. So it's easy for me to see the relation among these forces. I'm not going to draw P, so even though the problem shows that P is this way, but when I draw all these forces on this object, I'm going to consider like a point mass, okay? So I'm going to draw all the force starting from the center, so it's easy for me to see the relations, okay? So I'm going to draw the P, okay, starting from the center, and then that's the force P. So of course, if these are the only two forces on it, it's not going to stay there, right? Because if you break it into x and y, the P is going to have an x component, nothing's going to cancel that, okay? So there must be other forces on it. So now you see there's the surface, right? There's the surface here. So the surface is going to have a, if this is on the surface is going to have a normal force to it, right? Imagine if the wall doesn't have a normal force on it, it's going to be moving in this direction, right? So the wall needs to have a force stopping it from moving that way. So the normal force is always perpendicular to the surface, not always straight up. In this case, because the surface is vertical, so the normal force you draw should be perpendicular surface and in this direction, right? And then, because if you push this guy up, right? So at some point it's going to start to move up, right? So the force that keeps it stationary on this surface, there must be a static friction force and down, right? When you apply a force P very large, there must be a static friction force down. Okay, so imagine that if you apply a very large force up, it's going to tend to move upward, right? So the static friction force is always going to opposite to the attempting motion. Okay, so these are all the forces I draw. And then if I want this block to stay stationary on the wall, I would want all these forces cancel out. Okay, so that means I can still set up Newton's second law as we did before, and then the acceleration is 0, so I would have this equals 0, and then the net force in y direction equals mass times the acceleration, and then in this case it's still 0. So I'm going to set up my x and y coordinates and then break things into x and y. So obviously the best coordinate system here is just going to be the normal x and normal y we have been using, right? Because I can just call horizontal x and vertical y. So in this case I would have 3 of the forces on my x and y. So the only force I need to break, it's going to be the P force. Okay, so let's do that. So I'm going to break this guy into x and y. So this is going to be the x, px if I call it. And then there's going to be a y component, py. Okay, so now let's put all the components in these two equations we set up. This is still Newton's second law, right? So I would have the x component is going to be px, positive. Now normal force is in that direction, so I would call it negative. Okay, so these are the only x components, so that's going to be equal to 0. So that's still the first equation. Now the second equation, y component. Okay, py, it's going to be the y component up, positive. Now I have the static friction and the gravity down, so they're going to be negative to me in this equation. And again, because I want to keep this block stationary, net force is 0 because acceleration is 0. Okay, so I want to use these two equations to find the maximum P. So I don't have P here. I only have Px and Py. But remember, we can always write this component as the hypotenuse times sine cosine. So I will have P in these two equations. So let's do that. So Px, it's going to be this side. So I need an angle, right? I know the hypotenuse is going to be P, this force. What is the angle? The problem says the P force makes the angle theta with the horizontal, right? So it's going to be this line makes an angle horizontal with the horizontal theta. So the problem says this angle is theta. So this angle equals this angle, right? Okay, so P makes the angle theta with the horizontal. Okay, so that is right. Now, how do I write this Px and Py? Well, okay, I'm going to still use this right triangle. So hypotenuse, Px is adjacent to this theta angle given the problem. So in this case, it will be cosine. So Px, P cosine theta. Take a look at the direction, positive, in positive x direction. Okay, so I don't need a negative sign for this. Okay, so this is the x component. Now y component, P, so y is this side, which is also this side, so that's going to be opposite. So sine theta. Again, take a look at the direction, it's up, so it is positive to me in this coordinate system, so that's going to be these two expressions. Now I can replace this Px and Py. P cosine theta minus normal force equals 0. P sine theta minus mg minus fs equals 0. Okay, so these are the equations I got. Don't forget what we're doing. We want to manipulate this equation to find a value of P, the P max. So now let's see, how do we get the P max? So remember, as I said, if you apply force P on this block, you have a range, right? So you keep increasing the P force. At some point, it's going to start to move up, right? So why? Let's take a look at this equation. So if I increase P, so normal force gets larger. Okay, so that's easy to understand, right? You push it against this wall in this direction, you push harder and harder, the normal force is going to get harder, larger and larger. Okay, good. Now take a look at the second equation. I'm going to increase this equation, right? But I still want this object to be stationary, so these two equations are always going to be satisfied, right? Newton's second law. So if I increase this, then something must be increasing, right? Otherwise, this equation is going to be wrong. Gravity doesn't increase, right? Mass times 9.8, gravity is also always a constant for the same object. So then this guy must increase to satisfy this equation, right? To make sure the net force is still 0. So that is why the static friction force is going to change. And static friction force, we know that. It will change, right? So when does the P reach the maximum, okay, but still keeps the block stationary on the wall? That's when this guy has reached the maximum, right? You see that if the static friction has reached the maximum, and then you increase this guy, okay, a little bit more, then this static friction force in the mass is going to be smaller than this component, so you cannot keep this block on the wall anymore. So it's going to start to move up. So the maximum P is going to occur when the static friction force has reached the maximum. Okay? So that's how we figure out when this P occurs, right? So the P max is going to occur when Fx has reached the maximum. Okay, so now I can use this value to plug it into these two equations and then find the P max, right? Because these two equations are still satisfied at the critical point, okay? So now for P max, then we would have this. When P has reached a max, the first equation still true. It's not going to change because the normal force can still increase. Now the second equation, negative mg. So now the static friction force has reached the maximum, right? So that's the critical point. If you keep increasing the P force, now it's going to start to move because this guy cannot increase anymore, okay? This is the best it can do, okay? So we can, you see that now we can use these two equations to find this P max, okay? How do we find the P max, right? The easiest way is going to be this. Right. The first equation, you see that if I have the Fn and cosine theta, I can just go ahead and rearrange that to find the P max, right? Because I would just get P max equals normal force divided by cosine theta. Okay? But I don't have normal force, okay? Well, don't forget there's another equation I can use, right? So how do I use this equation? If I can use this equation, find expression for normal force, and then I can plug it in and find this P max, right? So let's do that. But I don't have the normal force in this equation. Okay, that's when we make use of this theory, right? The static friction force equals mu s times Fn. Okay, so the second equation is going to become P max sine theta minus mg, right, minus mu s normal force equals 0. Okay, and then you see that you can solve this equation to get expression for Fn. And then you plug it into that equation, you can solve for P max. But if you rearrange this equation, you will only get expression for Fn as a function of P max. You see that? Because you don't get P max, okay? If you want to find Fn, you need P max. But if you want to find P max, you need Fn. So it looks like this is circular, but you don't need to solve these two numbers separately, right? What do you do with this? You're going to find this as a function of P max. You plug it into the first equation, okay? So you don't even need to rearrange this equation. Minus Fn equals 0. So you don't even need to do it that way because you don't have the number for Fn. You're going to plug this equation into the first equation. Then you will get a complete equation on only P max. So you just go ahead and solve that equation, right? That's how we all solve like x and y in two equations, right? You substitute. You find expression, say, for y in terms of x. Then you plug it into the second equation. Then you get rid of y. You only have x. Then you go ahead and then solve that equation, okay? And then you go back and then you use the expression you found for y. You can solve for y. So that's how we solve two equations for two unknowns. So it's the same idea here, right? But the symbols are different, right? So if you look at these two equations, actually the x and y are going to be the P max and Fn, right? Everything else is a number. Even though we have a lot of symbols here, okay? Owning P max and Fn, they're unknowns. So you just solve for them, okay? So that's how you find the P max. Okay, so I'm going to leave it for you to finish this part. But that's only one value, right? That's only the upper value, right? Upper band. We also need to find lower band. But if you have done this, the lower band is going to be very similar to this. Okay, so you're going to draw, let's draw the Ferber diagram when the P is very small. Okay, so I'm going to still draw this gravity down. Okay, now the P force is very small in that direction. Okay, now do we still have normal force in this case? Yes, we do. Okay, because if there's no normal force, the block is going to move in that way, right? And it's not happening because the normal force is in this direction. Okay, and then imagine if you apply force very weak, very small on this block, it's going to tend to slide down, right? So you can try that, right? If you apply force and then you keep decreasing the force, right? So that means it's going to have a tendency to slide down. So the static friction force is the force that stops it from sliding down. So static friction force must be up in this case, right? So the static friction force changes direction, right? If the P force becomes very small, because now it has a tendency to slide down, okay? Now everything else is going to be the same. You still break this P force into x and y direction, okay? So you're going to still break it into x and y, so you still get px and py. Okay, you're going to still set up net force in x direction equals mass times acceleration, which is 0. And then you set up net force in y direction, mass times acceleration in y direction 0. okay? And when you set up these two equations, you're gonna see that the only difference that now you have a different sign for this fs, right? All the symbols are gonna be the same. You only have the fs now in y direction up, so it's gonna be positive. So that's the only difference between these two equations you're gonna set up and these two equations. So literally you would just have a opposite sign for fs. And then you're gonna do the same thing, okay? No, let's finish this. So we're gonna do this, right? So in x direction, you're gonna have px, which is px component minus fn equals 0. So this doesn't change, right? And then py plus fs minus fg equals 0. And if you compare this with these two equations we just found, the only difference is this sign for the fs. And then this is still going to be p cosine theta minus fn equals 0, p sine theta plus fs minus mg equals 0. Now you see that if you keep reducing this guy, okay, so this normal force can also decrease, so that's no problem. To take a look at the second equation. If you keep reducing this guy and then you still want this equation to be satisfied because you still want the block to stay stationary, this graph is not going to change, right? So this guy is going to increase, right? Because if you rearrange this equation, what do you get? You get p sine theta plus fs is going to be equal to mg. So this mg is going to be a constant on the right. So the sum, that means the sum of these two forces must be a constant. So if you reduce this guy, the p force a little bit, okay, the static friction force should increase a little bit in order to satisfy this equation. And static friction force can decrease and increase, right? We know that static friction force can always vary from 0 to the maximum value. Okay, so I want to find the minimum P I can apply on this block to keep it stationary. So the minimum value of P again is going to occur when the Fs has reached the maximum. So that means you cannot reduce this guy anymore because this Fs has already reached its maximum. It cannot provide you any number larger than that. So you keep reducing this. The sum of this guy is going to be smaller than mg, so mg is going to pull it down. Okay, so again, the P mean is going to occur when static friction force has reached the maximum. So that's how you found these two bounds, right? So you will still get, if you plug that in, P cosine theta equals normal force 0, and P sine theta plus the static friction force is going to be equal to mu s times Fn. So I can plug it in. So this should be P min. P min. Right? Mu s Fn minus mg equals 0. Okay? So that's going to be these two equations. Now you can do the same algebra. You write Fn in terms of P min from the second equation, plug it back into the first equation, you can find P min, right? You're going to have one equation on one unknown. You can solve for that. Okay? So now you can finish the algebra, okay? See if you can find these two values. Now let's take a look at this equation, okay? If I want to find the P max, what do I do? You rearrange the second equation, what do you get? You want to get a normal force in terms of P, so that's going to be equal to P max sine theta, right, minus mg, okay, divided by mu s. Okay, so that's what you got. Okay, or what you can do is that you can write PN. Okay, so that's an easy way. The easier one is this. You use this equation to find, so that's easier, okay? find Fn equals, but either way you will get the right answer, right? Either way you get it right. The idea is the same. You just write Fn in terms of P and then plug it into the other equation. So if you do this, then let's see. So I'm gonna find Fn using this equation and plug it in. Then what do you get? You would get P max sine theta minus mg, right? Minus mu s times P max cosine theta equals 0, okay? And then if you write Fn as a function of P max using this equation and plug it into that equation, you will get the same equation, right? You will get the same equation, okay? So it's just going to be a little bit different. Now, what are we solving? We're solving for P max, so everything else is a number to us, right? So I'm going to just put P max together, put these two terms together, and factor out P max. I get sine theta minus mu s cosine theta, and then move this constant mg to the right. Okay, now you see that if I divide both sides by this factor, I get P max. And don't forget all these symbols, they are just numbers, right? Okay? Minus mu s cosine theta. Alright, so now you can use the numbers from the problem, right? The mass is, the mu s is this, the mass is 6 kilograms, and the theta angle in the question is 40 degrees. That's what the problem of 50, I'm sorry. Theta angle is 50 degrees. You plug all the numbers in, so the upper bound is going to be 02.6 newtons. So that's the maximum P you can apply. If you apply a force like 103 newtons, no, it's not going to stay there, it's going to start to move upward. Okay, so that's the maximum value, that's the maximum force P you can apply on this block. And then you do the same thing. Okay, the easiest way you use this to write Fn in terms of P min cosine theta. You plug it in, you're going to solve for P min. So at the end you will get an expression very similar to that, but the only difference is that the negative sign at the bottom becomes positive. Okay, if you finish this algebra, this is what you're going to get. Now, plug all the numbers in. If you plug all the numbers in, this value is going to be 61.3 newtons. All right, so our conclusion is this, right? So the P value should be between these two numbers in order to keep this block stationary on this wall, okay? If you apply any force larger than this, it's going to start to move upward. If you apply a force smaller than this, it cannot keep this block there. The gravity is going to pull it down, okay? So this is this question. So we have finished the static friction. Now we're going to move on to kinetic friction. So if you apply force on the object and it's moving, so the friction force is kinetic friction, right? And then we have seen the simulation. If you remember the simulation on slide 4, so the kinetic friction is going to be almost a constant, okay? It's going to be almost a constant. So, and then we still have an empirical equation for kinetic friction, okay? And it's very similar to the equation for the maximum static friction, okay? So the kinetic friction is this, mu k times the normal force. So mu k is called the coefficient of kinetic friction, okay? But these two equations are different, okay? Remember, this equation tells you the friction as long as this object is moving, okay? So the static friction force So if the problem asks you, or if you need this kinetic friction force, you multiply them together, you will get the value, okay? But if you want to find the static friction force, as I said, the actual static friction force, you can't just say, I'm just going to multiply these two numbers, because these two numbers, if you multiply them together, you only get the maximum, right? Only the maximum is something you can predict. If you need to know the actual static friction force, you're going to have to set up Newton's laws and then rearrange equations. You can find the static friction force, right? So the actual static friction force, if the problem doesn't say it's already, or it doesn't imply it's the maximum, then you're going to use other forces to find it. Kinetic friction force actually is easier than this, okay? All you need to do is just find the normal force and then multiply that by the coefficient, okay? So that's the difference between them, okay? You can only use this equation to find the maximum static friction force, okay? They are very similar, okay? And then mu k, so for the two surfaces, okay, the mu k, the coefficient of kinetic friction, is usually smaller than this coefficient of static friction. So that is why, okay, in our experience, I believe that everyone is going to agree that it is harder actually to set something to move than to keep it moving, right? If you want to set something in motion, it's actually harder, okay, than keep it in moving. Once it has started to move, you can feel it's a little bit actually easier than starting it to move, okay? That's because this mu k, for the same two surfaces, the mu k is usually smaller than the mu s, okay? Now again, how do we determine this mu k? Like this mu s, there's no fundamental theory to help us predict this mu k. The only way you can find mu k for any two given surfaces is to do experiments, okay? So like this mu s. So if you want to determine the coefficient of kinetic or static friction between any two given surfaces, you have to set up an experiment. You can use the experiment to determine that. There's no fundamental theory to determine the coefficients for you, okay? So again, I'm going to show you a very simple experiment that can determine the mu k, the coefficient of the kinetic friction between two surfaces. So take a look at the experiment on slide 10. So this is very similar to the experiment we used to determine the static friction coefficient, okay? The only difference is this: we're going to have this M1, we're going to have two blocks. We're going to put this M1 on top of this, on this incline. And we're not going to raise the incline. So the incline is already fixed, the angle is fixed, okay? It cannot be changed. But we're going to connect M1 to another block, to another mass, okay, on the other side, okay, and then through a pulley, okay? So that's what happens, okay? And then how do we use this experiment to determine the coefficient of kinetic friction between M1 and the surface? So we still want to determine the coefficient between M1 and the incline, okay? So this is M1, okay? So it's connected to M2 through a string over a pulley, okay? And this incline has an incline angle alpha, and that's not going to change. We're not going to change that angle. So what we're going to do is this. So of course, if you place a mass here, so the mass is going to pull the string is going to pull M1. But this M2, if this M2 is like very small, okay, then the friction force is going to still keep this M1 on the incline, not moving, right? Say this is very, very small mass. And then what you can do is this. You can increase the mass of M2, okay? And then you can increase this mass because you can add things up, right? You can add masses up on this M2 until you find that at some certain mass, you're going to do that very carefully, okay? At some certain mass, then this M2 is going to pull this M1 up incline at almost a constant velocity, okay? So when it's moving at almost a constant velocity up the incline, then you can again set up Newton's second laws, and then now because the friction has become a kinetic friction, so you can use Newton's law, still Newton's laws, rearrange these equations, you can find an expression for this mu k. So that's our goal. That's what we want to do. So we're going to adjust M2 until we find that M1 starts to move up the incline at almost a constant velocity. Okay, so that's what we want to do. Now, okay, so let's see how we can use Newton's second law, again Newton's second law, to find expression for the mu k. Now what we're going to do is this. So I'm dealing with forces, velocity, acceleration. I'm still going to draw a further diagram and then use the break it into x and y, break forces into x and y, set up Newton's second law, and then rearrange that equation. So because M1, let's draw all the forces on M1. Gravity down, right? Normal force, again, remember perpendicular to the surface, not always straight up, right? And then, of course, there's a tension from the string on it. Okay, parallel to the string, right, and pulling it that way. And then if M1 is moving at a constant velocity, there must be a kinetic friction on it, and then opposite to its motion, right? So that's going to be all these forces on it. So if the M1 is moving at a constant velocity and you set it up, you're going to still have net force in x direction equals mass M1 A1x equals 0, right? Net in y direction A1y still going to be 0, right? Remember, constant velocity also means 0 acceleration, right? 0 acceleration, so I still get 2 zeros here. Now let's see, how do we find these x and y components? And on an incline, as I said, the best coordinate system we usually use is going to be this one. Right, so I call parallel x and then perpendicular y. If we use this x and y, we can break less forces. We're going to find a lot of forces are going to be on this x and this y. Right? In this case, you see normal force, tension, kinetic friction, they're already in x and y. So the only force I need to break is going to be gravity. Okay? So the gravity, you break it into x and y. We have done that, right? When we were solving the problem with static friction. You're going to break it this way. This is M1Gy, and this component is going to be M1Gx. Okay? Now let's put everything together. X component, I'm going to have T positive, M1Gx negative, so I have a negative sign. Kinetic friction, negative, and that's it. I only have 3 components in x direction, so I'm going to put a 0 on the right because acceleration is 0. It's moving at a constant velocity. That's what I'm going to do in that experiment. Now, a y direction, I would have normal force, and then the other one is just going to be M1Gy. Okay? And that's it. I only have 2 components in y direction. That's going to equal to 0. And then we know how to write M1Gx and M1Gy, right? As I said, you're going to transport this angle to this right triangle, and we have done that, okay? So you can take a look at the what we did in that lecture. Actually, this angle is going to be incline angle. If the problem tells you the incline angle, this angle is the incline angle. So you will get the x component, it's going to be gravity times sine, right? So that's going to be opposite to alpha. I need this x component. Minus, now fk, it's always going to be mu k times n, fn. So you don't need to make it maximum, right? Because that's already always the kinetic friction. So that's going to be the first equation. Now the second equation is going to be normal force minus m1g cosine alpha 0. Okay, so now we have this mu k. Don't forget what we're doing. We want to use this experiment to find mu k between the m1 and the incline. That's our goal, right? I already have mu k here, so if I have everything else, I should be able to rearrange these two equations to find these mu k. So let's see. First of all, Fn, this equation I can solve. Fn, normal force is going to be m1g cosine alpha. So if I have these two masses, m1, m2, and alpha, so these three guys are going to be something I can measure, and this is a real experiment, right? Because you're going to know m1, m2. You're going to measure these two guys in a mass scale if you want. And alpha angle, you can also measure that. Okay, so m1 is not something you should worry about. And then this thing, so you can calculate in this experiment. If you have done your measurements, you measured m1 and cosine alpha angle, so you can plug it into the first equation. And then this thing, again, m1 and alpha angle, if I have measured them, I have these two values. But t, you don't know t in this problem, in this experiment, right? Remember, you don't know the tension in this string, okay? So you have to find a way to find out this tension t, okay? That's when you use m2, okay? If you use m2, what do you get? Let's draw a Ferber diagram on m2. So I'm going to isolate m2. Gravity down, and there's a tension up, okay? And then because this is the same string, so the tension is going to be the same everywhere, okay? So that's an assumption we're going to use in this class, okay? So if it's the same tension, okay, if the same string, the tension is always the same everywhere, okay? So, and then if this is the tension, so you can set up Newton's second law for M2, okay? A lot of people, I should warn you, they would just write down, oh, T equals M2G. This is not always true, right? You can't just see that, oh, I see two forces on it, they're going to cancel, right? What is the motion of M2, right? Is M2 at rest, or moving at constant velocity, or moving with acceleration, right? So you should always do that using a law, using Newton's second law, right? So if I set up Newton's second law, I would do this. Net force in y direction equals M2A to y. And what is the acceleration of M2? Well, if M1 moves up the incline at a constant velocity, M2 is falling at a constant velocity. So in this very special experiment, okay, the acceleration of M2 is going to be 0. But if you see a problem, the M2 is falling with an acceleration, or it's like rising with an acceleration, you don't just put a 0 here. You don't just assume these two forces are equal, okay? So don't make that mistake. When I draw a Ferber like this, I'm just going to assume they are equal. No, you haven't really considered the motion of M2. You always need to consider the motion of M2 and set up Newton's second law. Then you will always get the right answer. In this case, now you see that, okay, now I can do T minus M2G. That's a net force in y direction. This is up, this is down, right? And then because of the acceleration 0, I can write down T equals M2G in this very special case, right? But this shouldn't be true for any question, okay? When you have a tension grabbed on something, okay? So don't make that mistake. Now you see that, okay, now I can put everything together in this equation, right? And then you can rearrange this equation to find this mu k, okay? So I want you to finish the rest of this algebra and then find the expression for mu k for me, okay? All right, so what do you get? So if I put everything into that equation, so I would get M2G, that's the tension, minus M1G sine alpha minus mu k times what I found for Fn, right? So this is the equation I got, and then I'm gonna rearrange this equation. The easiest way is that move this mu k times this whole thing to the right. Remember, only mu k is the unknown. You will measure everything else. Right? Then you just divide both sides by this coefficient of mu k. What do you get? So you will get expression for mu k, m2g minus m1g sine alpha over m1g cosine alpha. Now every term has little g, so you can even cancel out little g in every term. So we'll get m2 minus m1 sine alpha divided by m1 cosine alpha. Okay, now you see that if you set up a real experiment like this, all you need to do, measure m1 and measure cosine, measure alpha angle. So these two things, they're not going to change. But you're going to add masses on this side until you find a critical mass m2, so that it's going to pull this m1 at this on the incline at almost a constant velocity. So that's the m2 you're going to record. And once you have these three values, put them in this equation, you can find out this mu k between this m1 and the surface. So that's an experiment we can set up in a classroom. Of course, this is very primitive, right? This is not very accurate, but this is an experiment we can set up in a classroom to determine the kinetic coefficient or kinetic friction between two surfaces. Okay, so I'm gonna stop here for this video.